Hey everyone! So in this video we'll talk a little bit about how we can collect data in the health sciences. So where is this data that we're going to analyze actually come from, and how do we make good decisions about how to collect data? So in this video we'll talk about populations versus samples. What are the major differences between those? We'll also talk about some sampling methods, so how do we choose who ends up in our sample? We'll talk about experimental studies versus observational studies. So what are the major differences between those? How do we choose which type to use? And then finally, we'll go through some principles of designing an experiment, namely control, randomization, and replication. So let's start with populations versus samples. So in statistics, we refer to the population as the entire collection of individuals that a researcher is interested in. So the entire group that is available for study, or the entire group that we care about. There are some situations where we may be able to study an entire population. For example, the United States Census is an attempt to study the entire population. We attempt to reach every member of the U.S., citizenry or population. However, most often we end up working with a sample. So a sample just refers to a subset of the population for which we have data. So the data that we have most often is collected on just that smaller subset or that sample. So we have three scenarios here. For each one, let's identify the population of interest and think about some ways that we might collect data to form a sample. So here is the first research question. Do bluefin tuna from the Atlantic Ocean have particularly high levels of mercury, so much so that they're unsafe for human consumption? Our population here would be all Atlantic bluefin tuna. That's the group, or those are the subjects that we're interested in. The sample of tuna that we have collected would then be our sample. Second research question, for infants predisposed to developing a peanut allergy, is there evidence that introducing peanut products later in life is an effective strategy for reducing the risk of developing the allergy? Our population of interest, all infants predisposed to developing a peanut allergy. Whatever that predisposition means or represents, that is the group that we care about. And then finally, does a recently developed drug designed to treat glioblastoma, a form of brain cancer, appear more effective at inducing tumor shrinkage than the drug currently on the market? Here, our population would be all patients with that glioblastoma, that brain cancer. That's who we're interested in. Now, samples are most useful to us. They tell us the most information about a population when they're representative. What that means is that every characteristic that could be represented from the population is in approximately equal proportion as you find it in the entire population. So for example, a sample that is representative based on gender would have an approximately 50-50 split. A sample that is representative of college students based on class standing would be about 25% freshmen, 25% sophomores, 25% juniors, 25% seniors. Please ignore the dog drinking water in the background of the video. Now let's take a look at an example here. Suppose that the quality improvement team at an integrated healthcare system is interested in learning about how members of the health plan perceive the quality of the services offered. So based on what you already know, what might be a good way to take a sample? What might be a bad way to take a sample? And I'll ask you about this a little bit more in class, so be brainstorming between now and then. So let's take a look at some ways or some techniques that we can choose our sample from a population. This first one definitely falls into the not ideal category, and that's a convenience sample. Convenient samples come from individuals who are either easily accessible or more likely to be included for whatever reason. We just choose whoever's convenient to us to be part of our sample. Obviously, these are going to be less representative. The people that surround us or that we have easy access to on a daily basis usually don't represent the entire population at hand. A better option would be to use something called a simple random sample. This is the gold star of sampling, but it's also the hardest realistically to attain. With a simple random sample, each member of the population has the same chance of being sampled. So, even if we are attaining that simple random sample, there can be some problems. One of these problems is non-response. So no matter what, if we try to contact a subject to participate in a study or an experiment, they might not respond, and then we've lost them from our sample. So a typical non-response rate for an email survey is more than 50%, and you've probably experienced this yourselves, getting a survey, deleting it nearly automatically. So in practice, less than half of the patients in our example will actually visit the website to do the satisfaction survey. So if half of those who respond indicate a negative experience, does this automatically mean that at least 25% of patient visits are unsatisfactory? Maybe, but probably not. Think back to your previous experience. When did you rate a product or give a review? Are you more likely to give a review if you are very satisfied, very unsatisfied, or somewhere in the middle? We tend to lose representation from that middle group. The people who tend to respond to surveys, for example, have strong opinions, either on the positive side or the negative side, and that can certainly affect the quality of our data. So what are some other sampling methods that we can use? Well, one very useful type of sampling is what's called a stratified sample. So the population is divided into smaller groups, which we refer to as strata, and then we are randomly selecting observations within each of these strata. So in our illustration, we'll pick 3 from strata 1, 3 from stratum 2, 3 from stratum 3, and so on, to make a sample of 18. In a cluster sample, the population is divided into subgroups or clusters, and a few clusters are randomly sampled. Please do ignore this image here. This is the incorrect image. I will post a link to the correct image online. What you should be seeing is, instead of subjects within each of these, maybe stratum 3 has been selected and stratum 5 has been selected. All of the members from those 2 strata or clusters will represent our data. So for the scenarios below, which sampling method would you recommend and why? Let's go through all 3 of them. So scenario 1, suppose researchers are interested in estimating the malaria rate in a densely tropical portion of rural Indonesia. We have 30 villages in the area. Each one is more or less similar to the others. Our goal is to test 150 individuals. So if these villages are all fairly similar, think about the practicalities here. We'll have to travel from village to village to collect data. We could go to all 30 villages, for example, choose 5 people from each village. That would give us 150. Or we could select 5 out of the 30 villages, test individuals there, and then we would have our data. So we could use, say, a cluster sample instead of going from village to village. Here's our second example. This is the email phone survey link that we've seen before. We can still use a simple random sample here. In order to use a simple random sample, we need what's called a sampling frame. We need a list of all of the members of the population that we can choose from completely at random to generate our sample. If we're looking at, say, customer data or patient data where we have electronic health records, we can generate that list of customers or patients and take a simple random sample fairly easily. So even though non-response may be a problem, we still want to go down that simple random sample route. For our third example, so let's say this healthcare facility is interested in following some reports of discriminatory treatment of minority patients, and they want to make sure that underrepresented minorities are well documented in their reporting. So in this case, we might use a stratified sample. We might go back through our patient's health records, look specifically for patients who are members of those underrepresented minorities, and perhaps oversample them to ensure that we are in fact getting representation from those groups. So now let's talk about experiments versus observational studies and when we might use each one. So experimental studies occur when researchers are directly influencing how the data is collected by manipulating the subjects in some way. So in an experiment, we are doing something to our subjects. We're requiring them to, for example, receive some treatment or take some drug. Generically speaking, we call those experimental conditions the treatment. So treatment doesn't have to be, for example, a healthcare intervention with patients. In an experimental setting, it's just what we're doing to the subjects. Contrast this to an observational study. In an observational study, we're just sitting back and watching. We're seeing how the subjects behave, what they think, what they say, what they do. We may interact with them in some way to collect data. So for example, a survey might be considered an observational study. But as long as that survey isn't manipulated from patient to patient or subject to subject, it's still observational. The problem with an observational study is that we can draw very limited conclusions. Because we're not interacting with our subjects, we aren't really controlling or manipulating those external factors. So we can only observe so much. Okay, so we have two studies here. We'd like to read through each one and determine whether or not they're experimental or observational. So our first study, researchers randomly assigned diabetes patients to two groups. In the first group, patients receive a new drug called taspaglutide. Patients in the second group receive standard treatment without the new drug. The researchers want to compare the rate of insulin release in the two groups. Scenario 1 is an experiment. We're directly manipulating our subjects to have them either take taspaglutide or the standard treatment. We are telling them what to do. We're assigning them something to do. So this is an experiment. Scenario 2, psychologists tested whether the frequency of illegal drug use differs between people suffering from schizophrenia and those not having the disease. They measured drug use in a group of schizophrenia patients and compared it with those in a similar sized group of randomly chosen people. Now we are comparing two groups, but this is an example of an observational study, and here's why. We're not assigning people to have schizophrenia. We're not assigning them to use illegal drugs. We're merely just observing, collecting the data. So even though we have two groups we want to compare, this is still observational. So let's finish this video out by talking about some principles of experimental design. So let's say you're going to design or critique an experiment. What should we look for? So there are three major principles that we always want to look for in an experiment: control, randomization, and replication. So first, control. The researchers are attempting to control or limit the influence of outside variables. We do this by standardizing the experimental conditions, so everyone experiences the experiment in the same way. Our second principle here is randomization. So we want to, if we can, randomly select our patients or randomly assign our patients to treatment groups to make sure that these groups are balanced with respect to the things we can't control. We hope that everything that is external balances out by this act of randomization. And then finally, replication. We want our experiments to be repeated on a sufficiently large sample of data. So let's dig into that idea of control just a little bit deeper. There are actually two ideas of control that we think about in an experiment. The first is control from the design perspective, where we're trying to minimize the influence of those outside features or those outside actors, keep everything as standard as we can. The second is actually what's known as a control group. So a control group serves as a basis of comparison by either receiving a placebo or a non-active treatment or a known treatment. So for example, if we wanted to study a drug that reduces the risk of heart disease, daily aspirin treatment is a fairly known treatment for preventing heart disease. It's sort of the standard of care or the standard recommendation. So aspirin might be our control treatment. It's our reference point or our comparison. The reason we like to incorporate this control over our experiment is because we want to minimize the effect of confounding variables. So confounding variables are external variables. We may have data on these, we may not, that are related to both the explanatory and response variable. So the classic example here is the link between applying sunscreen and skin cancer. It turns out that there is a link between increased rates of or increased usage of sunscreen and increased incidence of skin cancer. We probably don't believe that sunscreen is causing the skin cancer. There's an external confounder here, and it's the sun exposure. People who are exposed to the sun more tend to use more sunscreen. People who are exposed to the sun more tend to develop skin cancer at higher rates. So that's the real variable at play. Second principle of designing an experiment, randomization. In an experimental study, we can randomize in two ways. We can randomly select subjects to participate. That's the ideal, but that's not always possible. For example, say drug studies or new drug or vaccine trials. We need to have a volunteer group who's willing to participate in the study, so we can't select those at random. But what we can do is randomly assign the subjects to receive an experimental treatment. So we could randomly assign half the subjects to receive a vaccine candidate, half the subjects to receive a placebo. If we can, we'd like to randomize along both of these axes. If we can't, certainly one element of randomization is important, either randomly selecting our subjects or randomly assigning our treatments. What this does for us is help balance out the other factors. It helps avoid researcher bias. Finally, let's talk a little bit about replication. So replication in statistics has sort of an unusual definition or unintuitive definition. When we're designing an experiment, replication is just this idea that we want to have multiple subjects experiencing each of the treatments. How do we decide how many? Well, there are some statistical or mathematical tools that we can use. Oftentimes, we're actually balanced by practical limitations. How much of the drug can we manufacture? What are the FDA limitations on drug trials? That sort of thing. There is also this separate study or this separate idea of replication called a replication study. And that's this idea that a study that has been done or previously published should be tried again to see if the results hold up. Now, unfortunately, this is a somewhat new phenomenon in medical research, but it is yet another example of replication, repeating the experiment. However, when we talk about designing an experiment, I do want to emphasize here that replication for us means the number of subjects. So that's it for designing an experiment and the principles of experimental design, observational studies, and so on. The next video is going to be a little different. It will be a little longer. We'll start talking about some ways that we can begin exploring data. Have a great day.